Pleasure to introduce the next speaker from SMBO Center, and who's the director of the center. And please, I want to take your time because we have to end on time.
Yes.
We haven't lost any time.
So let me start by thanking the organizer for inviting me. So I have come here before, but this is in a new setting, in a new avatar, and I'm liking it as much I used to like it before. And I'm going to talk about some of the computer predictions on hybrid organic-inorganic perovskite. I come from SNBO's National Center for Basic Sciences, the institute which was established to honor the life and work of Professor S.N. Bose, in whose name half of the fundamental particles of this world, namely the bosons, are known. And I come from the city of Calcutta, now it's called Kolkata. And those of you who have not been to this city, so this famous book by Dominique Lapierre, which says that's the city of joy. So I invite all of you to my city to find out whether it's city of joy or not. And hybrid perovskite, in fact, this morning in the section of the presentation by the student, it was actually introduced. But just to remind you, we all know what is an AbO3 perovskite. So you think the structure of AbO3 perovskite, but the A cation being an inorganic element, you put some kind of an organic molecule there, as is shown here in this pictorial picture. And instead of oxygen, you can either have halides, which have been actually talked about, or you can also have some polyatomic anions. And it got into a lot of attention in recent time, precisely because of this discussion with this lead halide-based hybrid perovskite, and the discussion going on with their uses as their highly efficient photovoltaic cell vis-a-vis the low stability and also the toxicity related to the lead that was currently the focus of discussion. But in today's talk, I'm going to focus on a different class of materials where instead of lead, we will focus on this evergreen field, which I call is that of the transition metal. And there have been work done primarily by the person who is sitting here, the organizer of this conference, Tony Cheetham, where they really looked at all this transition metal-based hybrid perovskite and talked about really their multiferroic properties, which are primarily driven by the ordering and disordering of this hydrogen bond, together with the magnetism that comes from this transition metal. Is there more to explore? And what I'm going to tell you, computationally, we do find there is indeed more to explore. And I hope my talk will trigger some collaboration from the experimentalists, which I'm always looking forward to. So the first one that we computationally looked at is the spin crossover phenomena, which is very important, especially in molecular complexes, where you have a transition metal ion surrounded by some organic ligand. And if that metal ion is in the valence state of D4 to D7, then by making use of the fact that since the organic ligands are very flexible, they can be externally manipulated by things like light or temperature or pressure. The pressure can be chemical pressure or can be substrate with a magnetic field or even mechanical pressure, hydrostatic pressure, that's what I mean, which I will also show. There can be transition from a low spin state to a high spin state because this metal ion is in the coordination of the nitrogen atoms, which are basically given by all this organic ligand. And therefore, by changing this metal ion to the organic ligand bond length, one can basically trigger such a kind of phase transition. And it's attractive because this phase transition is also associated with the change of color of this molecular crystal. Now, the whole goal is, can this make this phenomena cooperative? That means that this spin crossover that happens, I'm sure, sorry. How do I go back? This red one, yeah, that's a little complicated. Yeah, so the whole idea is, can we make this phenomena cooperative? That means the spin crossover that takes place at a particular metal site by putting one of this molecule next to another and making them talk to each other. If this spin crossover happens cooperatively at all metal sites, then this spin crossover, instead of being crossover, becomes like a transition. And if you can make this spin state transition a first order phase transition, it can actually show up with a very strong hysteresis effect. Therefore, you can use it as a memory device. That's the idea. And the whole idea is, for example, you should have this transition that is happening there, which is at the ambient condition, and make the width of this hysteresis as large as possible. That's the whole idea, if you really want to make an application out of it. Well, so this is the basic energy scales behind such a spin crossover phenomena. So first is the octahedral crystal field splitting, and the second one is basically the Hund's exchange. Because at the low spin state, if you take the example of iron 2+, all the electrons, the 6 number of d electrons, they are at the T2G state, while in the high spin state, you have to really overcome this octahedral crystal field splitting and put 2 of the electrons at the EG state. Of course, this is energetically expensive, but it is helped by the Hund's rule coupling, because in this way you maximize the spin. So these are the energy scales at the molecular level. Now, if you want to make it cooperative, you need to bring in energy scales that are associated with an elastic interaction. So basically, the elastic deformation at one side should talk to the another side, and that is considered as one of the mechanisms to bring in cooperativity. The other thing which we talked about is also the magnetic exchange interaction, because when you are at the low spin state, take the example of iron 2+, again, it's a diamagnetic object with no spin, nothing, no moment. So therefore, there is no magnetic energy. So you start from a low spin state, heat it up, and go to the high spin state. There is no magnetic energy contributing. But if you are at the other limit, that you start from a high spin state and slowly cool it down to bring it to the low spin state, of course, the system will not like to lose its high spin state, because it will lose that magnetic energy. So it is basically the interplay of these two. Now, what are the candidate materials? One of the candidate materials are the coordination polymer, and you will really have a volume of literature talking about these coordination polymers, the spin crossover coordination polymers in 1 dimension, 2 dimension, 3 dimension, as is shown here, like a connected path. So what we are proposing is the following. The hybrid perovskite can be actually an alternative candidate for looking at such kind of cooperative spin state transition. And a few years back, together with my PhD student, Hrishit Banerjee, we made this computer experiment and indeed showed that there can be pressure-driven spin state transition together with this hysteresis effect. And for that, these are the systems we looked at. So they are all protonated amine at the A site, as you all know. So we consider 2 different kinds of this A cation. One is a dimethyl ammonium, another is the hydroxyl ammonium. And the manganese version of both these compounds have been synthesized, but not the iron one, at least not at the ordered phase. But we considered really the ordered phase, and if you really can make it ordered of this hydrogen bonding, you should be able to see this effect. So what we basically found that by applying pressure, we do have a transition from a low spin to the high spin, and with the critical pressure, which is about 3 to 4 gigapascal, and you can not only change the critical pressure, but most importantly is the width of the hysteresis is tunable depending on which kind of A cation you are putting at the middle. And I didn't have time to get into all the details, but we found it is primarily driven by the elastic interaction. The second example I have are of the 2D magnets. You can also make a very useful application as 2D magnets. Well, since the rise of graphene, as you know, there have been so many 2D materials that have been talked about. I show a few, like hexagonal boron nitrate, silicon, borofin, MOS2, the transition metal dichalcogenide family, the decorated graphene, the graphene, and many different properties have been talked about, like metallicity, of course, with the unprecedented mobility, topological property, charge density wave, some of the things Umesh just mentioned, superconductivity, Mott insulators in this twisted bilayer graphene. But what has been missing in the 2D portfolio until the very recent time is the magnetic order. By putting add atom on graphene by external means, there have been attempts to engineer magnetism, but what we are talking about is the intrinsic magnetic order. So the magnetic order, it depends on the dimensionality of the system, as you know from your undergrad training, that in the 3-dimension, magnetic phase transition can always occur at a finite temperature. For 1 dimension, there is no long-range order. In 2 dimension, the issue of magnetic long-range order is complex. If you have a Heisenberg model with a perfect rotational symmetry of the spin, then the Marmin-Wigner theorem says actually there is no phase transition, or the critical temperature is 0 Kelvin, because any amount of thermal fluctuation destroys that magnetic order. However, if you can introduce some amount of magnetic anisotropy, the Ising model is the other extreme limit where you are at the completely anisotropic limit, then the magnetic ordering is possible in the 2 dimension. And that's actually of potential importance in view of the low power ultra-compact spintronics application, and a few years back, that's basically the story in the Nature Nanotechnology, which says 2D magnetism gets hot. And this basically started with 2 back-to-back Nature paper, where taking this compound, the chromium, germanium, tellurium, by application of moderate amount of magnetic field, even at the bilayer limit, this material is found to be magnetically a ferromagnet with a TC something of the order of 20 Kelvin. And theoretically, they could even show that even at the monolayer limit, it's actually a ferromagnet. And the other one, the chromium iodide, that even experimentally at the monolayer limit actually shows a Ising type ferromagnetism and stable up to 45 Kelvin. So that has a lot of technological importance. However, since these 2 candidates, there have been many other proposals, and there is an urgent need to expand the list of the candidate materials. So it will be actually nice if you can expand this list, and can any of these hybrid materials be a choice? And from our computational exercise, the answer is yes. So you all know the perovskite structure, as we discussed, and you can make layered perovskite structure in the sense you make a cut from this perovskite structure and modulate this cut from the perovskite structure with some spacer, and that basically gives you what is known as this Framers, Rudolfson, Popper series. Now, since you can make this now put some spacer, there is no geometric constraint for how big an organic molecule you can actually put up. And people have done such a thing where they have basically a complete inorganic layer of different kind of metal halides, and separated by this organic layer, And where the organic layers, they put even like a bilayer, which are head-to-head or tail-to-tail, where basically this head group of the organic layer that makes a hydrogen bonding with this halide layer, while between this organic layer tail-to-tail, there is a kind of the van der Waals interaction. And these compounds, as I said, has been made. And the first group of materials are copper-based, which are copper 2+ based. And I don't know whether it's published, but these were synthesized in the group of Tom Palstra, where they had basically this layered structure of copper chloride. And in between this layer, they could put basically 2 layers of this organic ligands, and which is in this kind of this tail-to-tail fashion. And we found from the old literature, I mean, together with copper, there is also an example and report of chromium 2+. Copper 2+ is in D9, and chromium 2+ is in D4. Please note that. That is important. And such kind of layered structure has been also reported in the literature. Now, can you make 2D structures out of this? And we calculated for that purpose the cleavage energy. And we found that the cleavage energy, which is shown here, is actually 2 to 2.5 times smaller than that of graphene. So if you can make 2D structure out of graphite, making graphene just by a Scotch tape method, that thing should be possible also for these hybrid organic materials. And indeed, that is possible because we then found this paper in Science where they took this material, which is lead bromide with this organic ligand, exactly with this layer structure, and they could make this atomically thin 2-dimensional layered structure of this. So that is possible. Now, what about their magnetism? We found that if you look at the magnetism of the bulk structure, in plane, they are all ferromagnetically aligned, the copper spin. In between the layers, they are either anti or they are ferro, but this between the layer magnetic interaction is extremely small because they have to pass through this spacer layer. Now, what causes this ferromagnetism? As I said, that this valence configuration is important. They have copper 2+, which is Ian-Taylor active. They have chromium 2+ D4, which is also Ian-Taylor active. And because of this Ian-Taylor activity, you see that gives rise to 4 short bond and 2 long bond. And there is what is known as anti-distortive pattern. That means the long bond of the one octahedra faces the short bond of the neighboring octahedra. As a result of that, it promotes the ferromagnetism because orbitals of 2 different symmetries, they basically point towards each other. So that's the key for the ferromagnetism that is seen in these materials. Well, we made a modeling. We calculated the magnetic exchanges, which turned out to be ferromagnetic, as I argued just from the orbital symmetry point of view. And we also calculated the magnetic anisotropy. We considered even a generalized form of this anisotropy, which acts like a pseudomagnetic field in the Heisenberg model. And then solving the spin wave spectrum through a Lanxess method, we find for the copper system, the TC is pretty small, although it will ferromagnetically order some 2 to 3 Kelvin. But for the chromium system, the TC can be as high as 40 Kelvin, like in the same ballpark as the chromium iodide, if you apply a modest amount of magnetic field. Without the magnetic field, the transition temperature itself is 20 Kelvin. Well, in the remaining bit of time, I want to talk about the third example. We have also heard this morning about this vacancy-ordered hybrid perovskite. And what about the magnetic double perovskite with such kind of hybrid composition? Can one really think about it? Well, just to remind you, what is a double perovskite? You take a formula of AbO3, make it doubled so that it becomes B2O6. And since you have B2, then you can put two chemical elements like B and BO6, B prime, and then you have basically alternation of the octahedra of BO6 and B prime O6, giving rise to a kind of superstructure that you can make out of the perovskite structure. Now we want to play the same trick, but with this hybrid perovskites. Is that possible? And yes, people have thought about it. So I give you some of the references which are given here, where they have indeed put some organic protonated amine at the A site. And then they have used basically the cyanide as the linker. And since it is like you have this 1 plus and with the CN 1 minus, then you need to put a monovalent and a trivalent. And so they have put basically potassium in most of the cases and chromium or iron. Now, we want both of them to be transition metal, not with the potassium. And that's exactly the exercise we did. So we put at the A side the Ma plus, and we considered the cyanide as the linker. And then for the B and B prime, we set copper, because with copper, maybe it's possible to make it monovalent. And then in the B prime, we had choice of 3D, 4D, and 5D series, the entire series, and see what actually happens. Well, whether they will be formed or not in the perovskite structure, that depends on the tolerance factor. Now, when you calculate the tolerance factor, you have to assume the ionic sizes. Now, of course, the copper can be either 1 plus or can be 2 plus. So it can be either 1 plus, 3 plus, or 2 plus, 2 plus. And the ionic sizes will differ. So we calculated both considering 2 plus, 2 plus, and 1 plus, 3 plus combination. And we do find they are actually in the limit of where the perovskite structure can be formed. So following the work of Tony, we also calculated this octahedral ratio, and that also shows that indeed they are in the range where the perovskite structure is possible. So just as a side comment, since you are now considering the polyatomic ligand, which is like a cylinder, if you think of, then you have to really, when you are calculating the tolerance factor, that's really not the normal way, because you have to calculate, introduce the height of it and also the radius of it. And Tony actually worked out all in great detail. So thanks to all this work, so we could calculate that. Now, there are two possibilities which way this CN bond will be. Will it be linked the C to copper and N to B prime, or the opposite? In fact, both are possible. So a priori, you have no idea how they will be basically linked. And that's why it's very important to discuss with Tony, because he told me about this Berlin green, and where it is also with CN, and iron is either in low spin or in high spin, and the iron connected to carbon is in low spin, while the iron connected to nitrogen is in the high spin state. So that tells me that the covalency has a role to play, at least. And other than covalency, what you can think of is the electronegativity. So that's all we did. So the first exercise was a simple exercise where we basically calculated the formation energy considering the C linked to copper and B prime linked to nitrogen and vice versa, and compared their energy. And what we find is pretty interesting. In the 3D series, except with the exception of chromium, the B prime N is always favored. That means the carbon likes to link with the copper, while the N end of CN likes to connect with the other transition metal, namely the B prime. For the 4D and 5D, there is an interesting thing. While for the early transition metals of the 5D and 4D, the B prime N is stabilized, but after a while, the B prime C gets stabilized. So there is some kind of an interplay. And what we found, the interplay is the following, that for the 3D series, it's basically the electronegativity difference that matters, because the electronegativity difference between the transition metal and carbon or nitrogen, that is much larger than that of the copper, because these are all in the left of copper. While for the 4D or 5D, actually there is a transition that happens as you are moving across the series from whether it is larger than copper, carbon or copper nitrogen electronegativity to that of the B prime C or N electronegativity. But then it's the crystal field effect that dominates. To summarize, the upshot of this whole thing is that at the beginning of the series is the B prime N configuration that stabilizes, which is driven by the electronegativity effect, while towards the end of the series in the lead transition metal is the crystal field effect that becomes important. But for the 3D series, the copper being also a member of the 3D series, it is always the electronegativity effect that becomes important. So now we have figured out whether the C will connect or the N will connect, which end will connect where. Now we have to now answer whether it's 1 plus 3 plus or 2 plus 2 plus. So what we find at the beginning, again the same electronegativity argument, at the beginning of the series, it's always the 1 plus 3 plus that dominates, while towards the end of the series is 2 plus 2 plus that wins. So the color convention is the following. If it is 1 plus 3 plus combination, then it's green. If it is 2 plus 2 plus, they are red. But of course, there are certain exceptions, like vanadium. So why it's like that? Because vanadium 2 plus is D3, and if you have an octahedral crystal field splitting, that leads to half filling of the T2G shell, and therefore it gives you an extra stability, and overruling all this electronegativity rule. Similarly, for the rhodium and iridium, that's an exception. The rhodium 3 plus and iridium 3 plus, they both are D6 in their 3 plus, and being 4D and 5D, they are low spin, and that gives rise to a filled T2G shell, giving rise to an extra stability. So we understood that. Now, what about their magnetic properties? Well, we didn't calculate the magnetic properties of 2 plus 2 plus combination, because we thought maybe that will be disordered. To make this 2 plus 2 plus order will be a challenge. So we considered only the 1 plus 3 plus kind of combinations. And what we find, they all prefer an antiferromagnetic ordering. Simple, given the fact that we find that these are the basically combinations with copper that we considered, all in 1 plus 3 plus combination. And these are the materials which are with this D1 configuration. These are with D2, and these are with D3, as is shown here. And what we find that the D1 configuration gives rise to the largest value of the antiferromagnetic exchange interaction, while for D2 and D3, the values are much smaller. So why does that happen? So D1, that means you have one of the orbital occupied by one electron, and you have the orbital of the same symmetry that basically overlaps through a super exchange to give rise to a magnetic interaction, and which, according to this good enough rule, should be an antiferromagnet. In case of the D2, two different orbitals of two different symmetry are populated, and therefore you have competing antiferro-type interaction that basically competes with the antiferro. So ferro and antiferro, both the channel opens up, and what you see that the net interaction, although it's antiferromagnetic, it gets weakened by the competition from the additional channel, which is ferromagnetic. So, and we calculated basically the mean field TC. This is a mean field estimate, but still the TC, which is actually the TN, it's an antiferromagnetic order, it's about 70 to 100 Kelvin. So with that, I don't have any summary because I think it is up to the experimentalist to come to me, talk to me, so that in the next presentation, I can give a better summary, and I can tell you some of these has been made, some of these has been observed, because some of these already exist. So these are the collaborators, Peter Opinier and Sudip Chakraborty, who was both in Uppsala University, and Sudip is now a faculty in Allahabad, and I really benefited by working in the spin crossover problem. Manoranjan Kumar, my young colleague at SN Bose Center, and Hrishit Banerjee, my former PhD student, who is now in the University of Cambridge, they actually worked on looking at what makes this entire phenomena cooperative. Dhani Nafday, my former PhD student, who is now in Stockholm, and Dipayan being responsible for working on this 2D magnetism as well as on the double perovskite work. And last but not the least, a special thanks to the chair of this conference, whose work actually motivated me to start working in this fascinating area. Thank you very much.
Great talk, and thank you for being on time. Any questions? Anybody? Please, Tony.
Yeah, thank you very much, Tanusri, for a fascinating overview of these complex systems. It's a comment, really, because you said you didn't calculate the 2+2+ magnetic ground states because you thought they might be disordered. I think you might get a surprise and find that they order. We found in work we've been doing recently on formates that we can get ordering of 3+3+ formates.
I see.
And I wouldn't have believed it had we not actually done it and found it. And so I think in your case, I mean, one thing you could do maybe, it's a bit more difficult, but you could do the 2+2+ ones ordered and then see if you can estimate the difference in energy as to whether they're ordered or not. Obviously, this
that is possible, indeed possible.
It's more difficult.
We just didn't explore it too much because unless there is a feedback from the experimentalist, we are too nervous to do things, and we'll say we are doing things which are wrong. People will say they can never be made ordered, and the disorder will garbage the whole thing because these are all insulating materials. So the magnetic interaction is completely super exchange. So if you have like anti-side disorder, copper and B prime sitting at the wrong side, that will mess up things quite a bit. But I don't know how much of, there is a certain percentage of anti-side disorder till which the magnetic properties will be still kind of preserved. I don't know all that, so I'll be very happy to talk to you, and we'll be very glad to explore it further.
Well, and Paul Atfield has published one as well.
Yes,
just
with
recently, which is ordered.
Yes.
Yeah.
Yes.
So I think it's worthwhile. Thanks.
Any other questions from anybody? Please, in the back there. Yeah.
Thanks. That was a really interesting talk. I had another question about the Prussian blues thing. So, what were the compositions on your sort of final sort of summary slide about the showing the super exchange trends?
Sorry, I can't hear.
Sorry, what were the compositions of the Prussian blues you were looking at with the when you're showing the super exchange trends?
Yeah. So
is
it
still there?
possible to go back?
I don't know if it's still there. Oh,
Yeah, it's still there. Is this slide you are
Yeah,
talking
yeah.
about?
So I see you've got what, zirconium and hafnium.
So basically, the combinations we are talking about is like copper titanium, copper zirconium, and copper hafnium, which, according to our prediction, should be the most promising one with a high nail temperature.
Have you compared the stability of those to copper metal?
Yes.
Because, okay,
yes.
fantastic. Because, yeah,
Yes.
my immediate concern was that zirconium
I
3
didn't
is...
show you, but we
Yeah.
did consider their stability with respect to the copper metal. So we checked their thermal stability in terms of the stability with respect to this copper metal and others, and as well as the dynamical stability, which we did not show. But we don't know what will be the other competing phases if you start making them. So we really need to have input from the people making it.
The other, I think, complicating factor, which is also probably pretty interesting, is the tendency for defects on the particularly metal site vacancies, which are pretty ubiquitous. Obviously, depending on the A-site cation you use, you can suppress them to some extent, but that's obviously been a big challenge.
So the most important defect will be the anti-site defect, and that can be calculated, but we need the impetus from the experimentalists. Otherwise, it feels like, we are just going ahead.
Thank you.
Yeah, thank you.
Any last thought? One more. Please come forward.
Hello, ma'am. As I understand, you are trying to build hybrid perovskites using organic-inorganic components. So I was wondering if you have explored the polymers in terms of molecular weights, that what type of polymer and having how much molecular weight can fit in the vicinity of your perovskite?
Yeah.
So is there any limitation to the...
So that is what I have shown as a tolerance factor, where the size of this organic molecule enters. So you are very right that the perovskite structure depends on the cavity. In that cavity, what size can fit in, and that's given by tolerance factor. So that was calculated.
Does it depend on the molecular weight of the polymer as well?
Molecular weight?
Of the polymer?
I don't think it's more with the size.
Okay.
Everything is with the size.
So the size of the chain?
Size of the chain, as well as the organic molecule you are putting at the cavity.
Okay.
Yes.
So one more thing, you mentioned that the polymer that we are going to put inside must bond with the help of hydrogen bonding with the perovskite. So it is necessary to have the electronegative entities in the polymers?
Yeah. Yes. Yes.
Okay.
Yes.
Thank you.
Yes.
Any last question? If not, let's thank again.
Thank you.
Let's hope some of the experimentalists will actually be inspired to try.
There are so many experimentalists, so I appeal to them.
Thank you for finishing on time.
Thank you.
Okay.